Hi, everybody. Today we're going to do a second part two of of section 2.7. So let's and this is all about finding maxes and mins and that sort of thing. Anyway, let's take a look here. I'm going to switch cameras now. So here's an example. We have y is equal to ax squared plus bx plus c. As you know, this is a parabola. I want you to find the vertex. Now, you learned how to do this in algebra with a certain formula. But we're going to do it now with calculus, and it's actually going to be a lot easier with calculus, believe it or not. So, or I think it's going to be easier. Anyway, let's find y prime. Y prime is equal to 2ax plus b. And I want to set y prime equal to 0 to find the critical numbers. And I get 2ax equals negative b. I bring the b over to the other side. And then I divide everything by 2, oh, look at that, by 2a. And I get x, x equals negative b over 2a, which is something which you should remember. You probably saw this as a formula in calculus. And in calculus, I'm sorry, in algebra. When you took algebra, you probably saw this as a formula. In algebra, they usually derive it with they do the what do you call it, completing the square, and that's how they derive this formula. But with calculus, we derived it very simple. Now to find the y value, this is a critical number. So the critical number is negative b over 2a. And as far as the y value, so y is equal to a times negative b over 2a squared plus b times negative b over 2a plus c, which would reduce to b squared over 4a minus b squared over 2a plus c. And this would simplify to, let's see, c minus b squared over 4a, which you then, I guess you could put into, if you want, you put into one fraction, 4ac minus b squared over 4a. And that will be the y value. So the critical point would be negative b over 2a and 4ac minus b squared over 4a. By the way, just in case you want to, and this is the critical point, which in our case is also the vertex. Because the vertex is going to be either going to be the highest point or the lowest. Oh, I'm sorry, we're not done yet. We have to show that this is to show it's a vertex, we would have to show that it's a max or a min, because vertexes are either maxes or mins. Let's just show that. So now the easiest way in this case, I believe, especially since we don't really know, the easiest way is to use the second derivative test. And I'm going to let y prime, let's find y prime. Y prime equals, let's see, y was that. So y prime is equal to 2a. Well, a is positive, then we have a min, and if a is negative, then we have a max. Remember, if a is positive, that means the function is concave up, which means a is positive means it's concave up. So the vertex is going to be a min, and if a is negative, it's concave down. The vertex is a max. Either way, it's a vertex, and it's either a min or a max. And that is very awesomely cool. And this is a great formula already. Let's look at another problem. Y equals 2x cubed minus 15x squared plus 24x minus 7. And I want to find the extreme. And I want to use this time, I want to use the second derivative test. Just to show you how fun and easy it is to use. Alrighty. So we're going to find y prime. Y prime is equal to 6x squared minus 30x plus 24. I'm going to set that equal to 0. And I'm going to also divide everything by 6. So this gives me x squared minus 5x plus 4 equals 0, which of course this factors into x minus 1, x minus 4. So my critical numbers are 1 and 4. I'm going to test each one to see if it's a max or min or neither. What we're going to do is we're going to take 1 and we're going to take 4. We're going to plug that in for x. Well, which x? Do I plug it into the x of this equation? Do I plug it into x of that equation? The answer is, anybody know? The answer is neither. We're gonna plug it into the second derivative, but first we have to take the second derivative. So y prime is this right here. So y double prime equals 12x minus 30. And I'm going to plug in x equals 1. I'm going to plug in x equals 4. And when I plug in x equals 1, I get 12 minus 30, which is negative 18. So since it's negative 18, that means it's concave down, which means I have a max. And when x equals 4, I get 12 times 4 minus 30, which is 48 minus 30, which is positive 18. And positive 18 means since it's positive, it's concave up, and it's a min. So now, what is the critical points? The critical numbers are 1 and 4. What are the critical points? Well, I have to take 1, and I have to individually take 1, and then I have to take 4. I have to plug them in for x. But which x? Do I do this x over here, that x over there, that x? Which equation? A lot of equations here with x's here. Which equation is it? What do you say? Pause the video, think about it, and then let me know. Okay, time's up. The answer is I plug it into the original equation, because that's what I want to find. I want to find the max and the min. I want to find the point, the critical point in the original equation, so you plug it into just plain y. So for x equals 1, I have y equals 2 minus 15 plus 24 minus 7. And that's going to be 26 minus 21, which is 5. That's right. 2 minus 2 minus 22. I think I made a hold a second. I think I made it. Yeah, I did make an error. That's it's actually 4. Okay. So therefore, my first critical point would be 1, 4. That's a critical point. My next critical point would be, I'm going to plug 4 in. So I get y equals 2 times 4 to the third minus 15 times 4 squared plus 24 times 4 minus 7. And that would be, that equals negative 71. So my second critical point would be 4 comma negative 71. That's my second critical point. So so there you go. Very beautiful and lovely example. And I have to say it's up to you. The first derivative test, second derivative test, they both work. They're both fine. Each one has its advantage. There's something nice about I guess something nice about the second derivative test. You don't start breaking up intervals and test points, all other kind of stuff. You just take the critical numbers and plug them right in. The only part that's a little bit more work with this that you have to go and take a second derivative. So it's up to you. Both these tests work, and let's just keep on seeing some more examples. Okay, everybody, now we want to find global extremes. So first I want to just show you, I'm going to share my screen with you. So I want to show you a little bit about the concept. So if you want to find global extremes, you see, because a lot of times if you want to find like the most profit, you want the biggest profit. You see, the critical numbers will give you a local max or a local min, but it may not be the local max may not be the overall max. I want to find the overall max. So how do I do that? How do I find it? I showed you how to find local. How do you find global? Well, it's really, in practical terms, it's really not such a big deal. You're really just going to look at all the different, you're going to look at all the critical points, and you're also going to look at the endpoints, and you're going to see which is bigger. In other words, if one of the critical points is bigger, then that means that local max is also an absolute max, if that's the biggest number. But if one of the endpoints is bigger, then that's the absolute max. It's really, in practical terms, it's really very straightforward, very, very straightforward. For example, this guy right there is a local max, but it's not as high as the endpoint. This here is a local min. It's not as low as that endpoint. This looks like it was probably some kind of critical number, even though it kind of looked like looked like it kind of flat and then it continues down. So maybe one of these critical numbers, which is not a max or a min, but what's the truth is we're fine. The point is we see that I could even throw this into the mix, but because I just want to know if it's higher or lower than anything else. So the global max or the global min is going to be either at a critical it's either going to be at a critical point or it's going to be at an endpoint, and that's all I'm going to do is just compare. So now let me give you an example. So I'm going to switch back to the other projector, the other camera, I mean, and here we go. We'll do a nice little example here. What I'd like to do now is find the global max and the global min for y equals x cubed minus 3x squared minus 9x plus 5, and x is the x is restricted between -2 and +6. So all I'm going to do is I'm going to find the critical numbers, which is I'm going to take y prime, and y prime is going to be 3x squared minus 6x, and then minus 9. Which is, and this is equal to 3 times x squared minus 2x minus 3. So y prime equals 3 times x plus 1 times x minus 3. So my critical numbers are -1, 3. So all I have to do is just take the following numbers. I'm going to make a XY table here. So I'm going to look at -2 because that's one endpoint. -1. I'm putting this in size order. Not that it really matters, but I'm putting the numbers in size order. And then 6. I'm putting the x values in size order. Not that that necessarily makes a difference. Anyway, now I just got to plug these in, and I'm plugging them into where? Now, where am I plugging them into? I'm plugging them into here, to there, to there. I'm plugging them into the original y value because I want to find the maximum, the maximum, the minimum of the actual function. So this is y, which is equal to x cubed minus 3x squared minus 9x plus 5. And I'm just going to plug those numbers in, and let's see what we get. And I get the numbers. So -2 I plugged into the y. So I got -2 to the third minus 3 times -2 squared minus 9 times -2 plus 5. That came out to 3. Then I plugged in -1. I plugged in all these other numbers. And I got 10, -22, and 59. Well, obviously the biggest number here is 59, and the smallest number here is -22. So positive 59 and -22 are the biggest and the smallest y values. So the absolute extreme, so the absolute min is 3 comma negative 22. By max and min, I'm talking about the y value being a max and the y value being a min. And the absolute max is at 6 comma 59. And notice, of course, the absolute max happens at an endpoint. The absolute min happens at a local min. So that is how we do that. Our textbook makes an interesting point here that when there's only one critical point, if there's only one critical point and that critical point is a max or a min, then that local max or min critical point has to also be a global max or min. And the reason is because if this max is the only critical point, well, that means the function is going to go down forever, because if the max is not the absolute max, in order for an endpoint to be higher, the function would have to turn around and go back up. But if the function would turn around, that would create another critical point, and this is the only one critical point. So that's kind of interesting. That's kind of an interesting, geometrical idea. I want to just knock off with a. Well, let's just. I want to do one more example, but first I want to look at just we'll lay some definition on you, and here we go. So to find global extremes, this is just define a global extreme. So the only places where a function could have a global extreme is at the critical point or the endpoint. If it only has one critical point, then it's a local extreme, then it's also a global extreme. If there are more than one endpoint, if there are also endpoints, find the global extremes by comparing the y values at all the critical points and at the endpoints. And when in doubt, graph the function to be sure. And this is just sort of a general summation of everything we've been doing. I want to do one more example, and then that'll be it for this video. If I were to ask you to find the global max or the global min of this function y equals x cubed minus 6x squared plus 9x plus 2. And we actually had this this exact function previously in our section. Well, if you look at the graph of it, that's the local max at 1, 6, and that's the local min at 3, 2. But you see, it goes higher up here. It goes higher up forever. And it goes lower down forever. And this function, I never said x is between this and that. I just said, I just gave you this whole graph up to infinity. So this function has no local max and no local min, because it just goes up and up and up forever. So that's the way it is. As a rule, if a function is if a continuous function is in a closed interval, it will always have an absolute max or min. They call it the extreme value theorem, but this is not a closed interval. This is defined over the entire real number line. Anyway, that is the story. It's been lovely and delightful and very thrilling. And we will see you. Actually, we will see you next time. As I fade out, I'd love to have some fade out music. I'm just showing you the extreme value theorem, that if f is continuous, and imagine the fade out music is playing. If f is continuous on a closed interval a comma b, then f attains an absolute max and an absolute min at some numbers in that closed interval. So as these examples show. Anyway, that's my fade out music. Bye, everybody. That's the end of this video. We'll see you guys next time. Bye.